All right, everybody, hello and welcome back. Today what we're going to do is we're going to take a look at what we call sequences and series. So the first thing we need to do is describe and explain what a sequence is. A sequence is an ordered list of numbers. And then we have an explicit formula, which is a formula we use to represent a sequence and find any term we want. All right, so we're going to take a look at a couple examples, and that should kind of help clarify what these things are. In this section, in this unit, vocabulary and notation is really important, so make sure that we are using the proper vocabulary when possible and our notation is correct. So this is a visual representation of our first sequence. So we've got our first image, our second, our third, and our fourth. Well, in here you could see we've got 1 block, 3 blocks, 5 blocks, and 7 blocks. So this up top, 1, 3, 5, 7, is going to be our sequence. All right, and really we'd have commas in between here. So this is a sequence. It's an ordered list of numbers, and what we're going to want to do is write an explicit formula. Write a formula that we can use to represent this situation, so then we can find out what would be the 7th term in the sequence, or the 100th term in the sequence. So as you might notice, these numbers in the sequence are going up by 2 every time. So most of us might relate that to a linear function. But it's a little bit different. So with linear functions, you can plug in fractions. You can plug in negative numbers. We can't really do that with a sequence. You can't do that with a list. With lists, there are only whole number positive values. So for example, you wouldn't have a negative second item in your list. You wouldn't have a 1/2 item in your list. You have the first, the second, the third, the fourth, and so on. So that means our notation here is going to change. We are not going to be using x. Instead, we are going to be using n values. Now, n is going to stand for our term number. So if we're looking for the second term, we should be able to plug in 2 for n and find out how many, in this example, cubes are going to be in that visual representation. Now, because this isn't a function, we're not going to use y. We're actually going to use a sub n. Now, this is going to represent the nth term. So again, sounds very strange, but because this is our nth term, that means a sub 1 is our first term, a sub 2 is our second term, a sub 8 would be our 8th term, so on and so forth. All right, but the rest of this is going to be pretty similar. Again, we're going to use different values, but it's okay for us to start using a linear equation to help us figure out what our explicit formula is going to look like. Now, in this example, our pattern is that we are increasing by 2, so that means that our slope, and I'll show that here. Sorry, this should happen on the other side here. Our pattern here is that we are adding 2 every time. So that means my slope is going to be 2. And now we just need to think about what initial value is going to work in this problem to represent this situation. Now, a lot of people are going to say 1. But the problem is, if I put 1 in there, that means I should be able to plug in a sub 1, so find my first term. But I end up getting a first term that is 3. And our first term is 1, so it's not actually going to be a positive 1. Instead, it is almost like visualizing what would come before our first term, which would be negative 1. So this right here is our explicit formula. Now, if I wanted to find my ninth term, a sub 9, I would take that explicit formula and plug in 9 for n, because n is my term number, and I would get 17. What that tells me, if I continue this visual representation, my ninth image would have 17 cubes in it. All right, so that's kind of what we're going to be looking at, but these patterns can look different every time. So for example, we might see something like this. So again, we have our first, second, third, and fourth image. These numbers are going to be 3, 6, 12, and 24. So it's a little bit different here, but our setup is going to be pretty similar. First thing we want to do is point out the pattern. Well, many of you probably recognize that we are going to be multiplying times 3 times 2 every time. So instead of using a linear function to kind of base our equation off of, instead we need to think about, okay, what type of equation multiplies to go from one value to the next? And the answer is going to be an exponential function. Now, again, we need to use some different terms here, so we're not going to use y. Instead, we're going to use a sub n, because functions and sequences are different. Instead of x, we use n, and now we can kind of just fill in our missing values. Now, our b value is going to be the pattern, and now our pattern is we are multiplying by 2, and I'll show that here, which we actually already have. And then I just need an a value or an initial term that's going to make this work. So what we need to think about is a sub 3 should represent our third term in this sequence. Well, a times 2 to the third. All right, well, that means we should end up getting 12, right? That's how many we have in our third term here. And then 2 to the third power is 8. So if we solve this by dividing by 8, we end up getting 3 over 2 is equal to a. So therefore our a value is going to be 3 over 2. And just to test this out, our second term, as we could see, is 6, right? There's 6 cubes in the second image. We should be able to do 3 over 2 times 2 to the second power. Well, if we do this, we get 3 over 2 times 4, which is in fact 6. So this is what our explicit formula to represent this sequence here is going to look like. Again, they're going to look a little bit different. It kind of depends on the pattern. A little bit later on, we'll specify some of these and we'll give you some specific formulas to use that will kind of help make our explicit formulas a little bit easier to find. Now, the last example I want to do is this one here, and we'll do it a little bit quicker this time. Here's our first image, our second, and our third. Well, since I'm running out of room here, we have 5 values here, 4, 5, 6, 7, 8 values here, 9, 10, 11, 12, 13 values here. So this is a pretty tough equation for us to kind of figure out. It doesn't really follow any of the patterns that we are used to dealing with. However, through a little bit of practice and exploration, we can find that the pattern is actually going to be our term squared plus 4. So, for example, 1 squared plus 4 is 5. 2 squared is 4, plus 4 is 8. 3 squared is 9, plus 4 is 13. So this is going to be our explicit formula. Again, it's a little bit more difficult in situations like this where it doesn't really follow one of the function patterns that we are used to seeing, but the more you practice, the better you'll get. And a little bit later down the line, we will get a little bit more specific in what type of patterns you might see. Now, the next thing we're going to talk about is a series, which is the sum of the terms in a sequence. So if we go back up here, the series in this example would be 5 plus 8 plus 13. Again, we could easily do those values there. 5 and 8 gives us 13. 13 and 13 is 26. So this series, where we are adding the first three terms in this sequence, has a sum, or a total, a value of 26. Similarly, we could do 3 plus 6 plus 12 plus 24. We are finding the series of this sequence. And then 3 and 6 is 9, plus 12 is 21. 21 plus 24 is 45. All right, so a sequence is an ordered list of numbers. And a series is when you take the sum, when you add together those values in your sequence. Now, we also use a notation to kind of help us out. It is called summation notation, where we have the Greek letter sigma. Redo that so it looks a little bit nicer. All right, and then what we're going to do is we're going to put our explicit formula right after. And then down on the bottom, we are going to put what value we first want to plug in, which tells us what term we're going to start with. So in this case, n is equal to 1, so that means my equation here is going to have an n in it, and I'm going to start by plugging in 1, so finding the first term. And then at the top here, I am going to put k, which represents the last term. So I'm going to start by plugging in 1 to this formula, then 2, then 3, then 4, then 5, then all the way to k. And then my summation value here tells me that I am going to add those values together. So this is our first example. We have m times m plus 1 is our explicit formula. What I want to do is plug in the value down here first. So I'm going to plug in 1. And then I'm going to plug in my next number, which would be 2. Then my next number, which is 3. My next number, which is 4. And then I'm going to go ahead and plug in 5. Now that's where I'm going to stop. So I started by plugging in the value they gave me on the bottom. And I went all the way to the value on the top. And now all I have to do is add them together. So the series, which is when I take the sum of the first 5 terms represented by this explicit formula, is going to be 2 plus 6 plus 12 plus 20 plus 30. So 50, 62, 68, 70. So the sum of the first 5 terms in the sequence represented by this explicit formula is going to be 70. What I just did is I found the series. I added together the terms in the sequence. Now, our situations might look a little bit different. Sometimes we're going to be given our summation notation, which you actually can do in a calculator, and I'm sure if that's what you wish, your teacher will show you how to do that. But we also might have a series represented like this. Now, this is a little bit different because instead I have the terms. I have the series listed out. So I have the sum of all of my terms. So this is my first term, second term, third term, fourth term, and so on. Well, I want to write this in summation notation. So I have my Greek letter. We're starting off with the first term. And I actually have, once again, 5 terms here. So I'm going to put a 5 on top. Now, don't let the 5 confuse you. Just because it was 5 over here as well, we could have 6, 7, 8, 9, 10, 11, 12 different terms. It really doesn't matter. It just kind of depends on the sequence or series you are provided with. So now what I need to do is I need to go ahead and write my explicit formula. So as you can see, many of us might notice that our pattern here is we are multiplying by 4. So that means I'm going to have my first term, my ratio, to the n power. Now, in order for this to work, I need to find an a value that would make it work. What I should be able to do is take this explicit formula, and let's say I want to find my first term, which is 4. And that means I want to plug in 1 for n, because 4 is my first term. And I can solve to find out that a is just 1, so I don't really need it in there. This is going to be the summation notation of the series described above. Now again, we could just plug this into our calculator. Many of you might say, hey, I could just add these together right here and not have to write the summation notation on the bottom. A little bit later on, you might not know all the terms in the sequence. I might give you the first, second, third, and then the 9th and 10th term, and leave out the middle ones, and you're supposed to figure out what the sum would be. So you can't just add them together. In this case, or in that case, I should say, you would want to use the summation notation to find the value of the series. All right, as always, thank you for listening. If you have any questions or concerns, please feel free to reach out.